All right, folks, this is our second lesson in our electricity unit, and this one is kind of a doozy, so I hope that you are ready and focused and good to go. Today we're going to be talking about electric force and electric potential. So basically looking at those electric fields that are generated when we get excess charges building up on objects and kind of looking at how they then interact with other charges that come along their way. So a few goals for today. First of all, being able to actually calculate electric force that exists between two charges that are somehow in contact with each other. We will define some terms, including one called electric potential, which is kind of related to our previous idea of potential energy with a little bit of a twist. And then lastly, we will dive a little bit more into electric potential because that's going to be useful to us when we start analyzing circuits. So we'll talk about how to calculate potential as well as how we can use potential to predict which way charged objects are going to move within a given electric field. Okay, so first of all, electric force. You may have noticed in our demos that we didn't necessarily need to have two objects directly touching one another in order to notice an actual attractive or repulsive force between them. So for example, when we had the two balloons that we charged either by rubbing them against each other or rubbing them against our hair, they didn't actually need to be touching. Even being near to each other, we could see them either pulling towards each other or pushing apart. When we played with the Van de Graaff generator, I'm sure that you noticed that there was a force exerted between, for example, the soda can and the Van de Graaff generator. Even when they weren't actually touching each other, we still saw the soda can get pushed away every time it gained a negative charge. So then what we can conclude is that electric force doesn't necessarily need to be exerted through direct contact. It can act at a distance. Now, the only other force that we have examined so far that similarly acts at a distance is gravitational force. So you're going to see that throughout this lesson, we're going to be constantly comparing electric and gravitational forces because they're actually super similar. Okay. One major difference between the two of them, just to get that off our chest right away, is that gravitation is always attractive. You're always going to be pulled down to the earth. There will never be a situation in which the earth is pushing you away, up and off into space. That would be unfortunate. Gravitation then is always attractive, always pulls two bodies together, whereas electric force, as I'm sure you have noticed, can either be attractive and pull two bodies together, as in the case of opposite charges interacting, or they can repel each other, as in the case of like charges. Now, if we then want to go on and quantify electric force, again, a lot of similarities to gravitation in that they both act at a distance. So let's return to the way that we calculated gravitational force and see if we can, develop a model to figure out what electric force will be like. So before, when we calculated gravitational force, we had this equation. So the force due to gravity is equal to some constant, in this case the universal gravitational constant, times the masses of each of our two objects interacting divided by the distance between them squared. Okay, so we've got constant times mass divided by the distance squared. Now it turns out the equation to calculate electric force is super similar. It's right here, summed up in what we call Coulomb's law. The electric force acting between two charges is equal to some constant. In this case, it's Coulomb's constant, which is 9 times 10 to the 9th Newton meters squared per Coulomb squared, times, instead of mass this time, we've got charge. So the charge of our first object in coulombs times the charge of our second object in coulombs divided again by the distance between them squared. So once again, we've got force equal to a constant times something about each of our two objects interacting. Before, for gravitation, it was mass. In this case, it's charge. And then we divide by the distance between them squared. So super duper similar to gravitation. Who'd have thunk it? What you might notice is We can use the sign of our electric force to determine whether the force is attractive or repulsive. So anytime that we've got oppositely charged objects, so one's positive and the other's negative, those two multiplied together are going to give us a negative number. Now we know that opposite charges attract, so what that means is that if we come up with a negative number for our electric force, we must have an attractive force. If, on the other hand, our two charges are both positive, or if they're both negative, either way, when we multiply them together, we'll get a positive number. So if we end up with a positive number for our electric force, we know that it must be repulsive, because that implies that both of our charges are similar, both positive or both negative. Let's see this in action. All right, so we've got two charges located 0.5 meters apart from each other. Our first charge is positive 2.5 microcoulombs. Remember this guy? Yeah, micro, which means times 10 to the negative 6. Okay. Now this charge is interacting with another charge that is negative 1.5 microcoulombs. We want to figure out how big is that force in between them, and are they attracted to each other or repelled by each other. So as always, gonna write down everything I know. Don't know the force, but I know Coulomb's constant, always gonna be the same, don't even have to think about it. My first charge is 2.5 microcoulombs. I need to convert that into coulombs. All I need to do in order to do that is add a times 10 to the negative 6. That simple. Same for my second charge, add a times 10 to the negative 6 to get it into coulombs, and I know the distance between them. Now from there, I can use Coulomb's law, electric force equals kQq over r squared, and just plug everything in. There's K, first charge, second charge, divided by the distance between them squared. When I plug that into my calculator, I end up with a total number of negative 0.135 newtons. So not very big for this small amount of charge. The fact that I got a negative number tells me that this force is attractive, which makes sense because we've got a positive charge and a negative charge. We expect them to attract each other. Okay. Now again, we said that electric force can act at a distance. Now to apply some old terminology to that, before when we first talked about forces, we talked about contact forces, forces that require direct physical contact between two objects to be exerted, and field forces. So what this tells us then is that electric force must be a field force. It can act at a distance. Now in order for a field force to exist, there has to be a field, duh. So that tells us then that in addition to, in the same way that massive objects create gravitational fields around them that pull things in, charges then also generate electric fields around them. And the way that we end up getting another object to feel a force from that object is to have it enter the electric field of another charge. Okay. So again, same way that we will feel attraction to the Earth if we are within its gravitational field, we can cause there to be an electric force between two objects by having them enter one another's electric fields. Now just to give you a sense of what electric fields look like, we've got a couple pictures here. What you'll notice is that the electric fields, kind of the same way that gravitational fields do, just emanate directly outward from whatever source charge we're dealing with, whatever it is that's creating that electric field. So no weird, freaky, curvy lines or anything, just stick straight outward. In order to remember this, you can also refer back to our Van de Graaff generator and the shape that either the pom-pom or your hair or anything that was in contact with that Van de Graaff generator took. We noticed that those hairs or pom-pom strings or whatever aligned with those electric field lines and stuck straight out, looking pretty awesome in the process. Okay. Now to continue on with our analogy to gravitation, you may recall that we were able to calculate gravitational potential energy of an object. That an object located in a gravitational field will have some energy stored up as a function of its position within that field. Okay. And when we drop an object at a certain gravitational potential energy, that energy can be converted into kinetic energy or what have you. Okay. Similarly, if we have an object, a charged object located in an electric field, that means it has a certain amount of electric potential energy, which can also be converted into kinetic energy, which we in this case call electrical energy, the energy of charges moving from one location to another on the basis of that potential energy. Now, here's where potential energy starts to break down a little bit. Okay, so let's continue on with this gravitation analogy. Let's consider we've got two planets, planet A and planet B. We don't know anything about those two planets. We take two objects, object A and object B, and we stick them on the surface of those planets. Okay. Now we measure somehow the gravitational potential energy of each of these objects on their respective planets. We see that object A has 30 joules of gravitational potential energy. Object B has 40 joules of gravitational potential energy. But we don't know anything else about our objects, about our planets. This is all we know. Maybe what we really want to figure out is some stuff about the planets, and in particular, which one has a stronger gravitational field. Okay? The question is, just based on this measurement, do we know enough to say definitively one planet has a stronger gravitational field than the other? Now, you might be tempted to say that planet B has a stronger gravitational field because there's more potential energy there. But that's not quite right, because if you recall, potential energy doesn't just depend on the strength of the gravitation on that planet measured by G. It also is going to depend on the mass of the object, not to mention its position. So the fact that object B has more gravitational potential energy could be due to a stronger gravitational field, or it could just be that object B is more massive than object A. Okay, I know that this is a little bit on the tricky side. Feel free to try plugging in some numbers and see how it works out, or ask me questions, obviously. But the idea here is that energy depends on so much more than just the field strength. It also depends on some specifics of the object located within that field, its mass, its position, etc. Okay, so if I measure the gravitational potential energy at a given point, it kind of tells me about two different things at the same time, both the field and the object itself, right? Now, in the same way, if I take some test charge and I stick it into an electric field and measure its potential energy, that energy depends on both the strength of the field and the number of coulombs in that test charge. Okay, so basically the potential energy is reflecting two things, so I can't really just figure out the strength of the electric field because it's also getting conflated with the amount of charge. So basically I need something else. Potential energy is not going to be enough for me to compare two different electric fields. I need something new that's going to allow me to compare the two without getting the specifics of the test charge that I used kind of conflated in there with that. Now, the new term that we use, and it turns out to be oh so useful, is electric potential, also known as voltage. Basically, what they do is that just tells us the amount of electric potential energy per Coulomb. It's kind of like if I wanted to figure out the gravitational potential energy per kilogram. Okay, it's basically just a way of dividing out the amount of test charge so that all I'm left with then is a reflection of the strength of my electric field. Okay, so again, we're basically just looking at the amount of electric potential energy per Coulomb. We call that electric potential. This way, it is a function just of the electric field and not of each individual charge that comes wandering into that field. Now, the unit that we use for electric potential, is the volt. A volt is equal to 1 joule per Coulomb because it's the amount of potential energy in joules per Coulomb of charge. So a volt is a joule per Coulomb. So that means then that if we wanted to calculate the electric potential at a given location, we would just take the electric potential energy of a charged object at that location and divide by the charge of that object. So let's see what that looks like. We've got a 0.0004 Coulomb charge. It's hanging out in an electric field. We've got a potential energy measured for it. We want to figure out the electric potential of that location. In other words, a way to kind of determine the overall field strength that will affect any test charge that wanders through it, whether it's this little 0.0004 Coulomb charge or like a 5 billion Coulomb charge. Now, here's what I know. I know the electric potential energy. I know the charge. I'm trying to find the potential. I've got a handy little formula on my side. Plug it in. Wha-bam. I determined then that the electric potential at that location is 125 volts. And that is a number that's going to be the same for all test charges that come through, no matter how many coulombs of charge they may possess. Now, this is useful in and of itself, but where it gets really useful is when we start being able to compare the electric potential of two different locations. As an analogy, if you were sitting on a staircase or standing on a staircase, probably more likely, and you started to lose your balance and you were going to fall, okay, the way that you fall depends on which way is going to give you the location of lower gravitational potential energy. In case you haven't noticed, we always fall down a staircase. We always go from a location of higher potential energy to lower potential energy. I have yet to see anyone fall up a flight of stairs. It is always downward. Okay? In the same way, any positive test charge in an electric field will always move from an area of high electric potential to an area of low electric potential. Basically, our positive test charge is falling down the stairs, going from high energy to low energy. Okay? So then a lot of times what we'll do is we'll look at the potential difference between two locations and then figure out which side is lower. That's the way that our positive test charge is going to move. Now, what's kind of funny about this, and this is another place where gravitation and electricity are a little bit different from each other. This is the direction that a positive charge will move, from high potential to low potential. But whatever a positive charge does, a negative charge is going to do the exact opposite. So what that means then is that a negative charge will move from low potential up to high potential, which is kind of like saying electrons fall up the stairs. It's kind of weird, but it works, so cool. All right. Now, when you heard the term voltage to describe electric potential, I hope that what came into your mind was batteries, probably, because that's one area where we see voltage in volts frequently. That's because electric potential and potential difference are very important to the functioning of a battery. So you may have noticed that batteries on either end have two metal plates. And those plates are actually made of different materials. And on the inside of the battery, we've got some acid. Okay, now, as the acid interacts and reacts with those metals, they're naturally going to have different buildups of charge on them. And those different charge buildups are going to create different electric potentials, different amounts of energy, basically, associated with them. Okay. Now, when you see like a 9-volt battery or a 12-volt battery or whatever, that's telling you the potential difference between those two plates. So a 9-volt battery then has a potential difference of 9 volts between one plate and the other plate. So maybe this plate is 15 volts and this plate over here is 6 volts. Okay. So we've got a 9-volt difference between the two sides. Now, once we plug this in, what we're going to find is that all these electrons over on the lower potential side want to move over to the side of the battery with the higher potential. Okay? And that basically is what powers all of our battery-operated devices, is the fact that those electrons are trying really, really hard to get to the side of the battery with a higher potential. Okay? Now, in the process, the way that we actually utilize this to help us is that we basically have them jump through all these hoops, we construct circuits around it, so that as they're trying to move to that area of higher potential, they also have to actually, power your device, okay? But basically, our little electrons are just trying to run home to the area of higher potential where they belong. Okay. Now, as a way for you to check yourself and see if you really got what you were supposed to get out of this, a few questions for you to ponder. First of all, we've been comparing electric and gravitational force and fields and everything throughout this whole lesson. Compare and contrast. How are they similar? How are they different? Second question for you to ponder. We talked about electric potential energy and how it was kind of insufficient and how we needed to define a new term called electric potential. What's the difference? They sound very similar, but they're not. Okay. Last question. We've got a little diagram here for you. We've got two plates located on either side here. Each one has a different electric potential. This one has 4 volts, this one has 15 volts. If I then take a proton and an electron and I stick them in the middle between these two plates, which way are they each going to go? Okay. So take a moment, feel free to pause as you ponder these questions, and when you are ready, we'll move on. All right. So first of all, just a few points of comparison between electricity and gravitation. There are many, many more. First of all, some points of similarity. They're both field forces, so they act at a distance. Both of them are inversely dependent upon the distance between our two objects. They're both, to calculate the force, we divide by the distance between them squared. We've got situations where mass and charge are kind of analogous to each other in terms of their effect on the overall force exerted by that field. One major difference that we mentioned before is that gravitation is always going to be attractive between two bodies. Electric force, on the other hand, can either pull two bodies together or push them apart. Okay. Second question. Our electric potential energy depends not only on the field strength, it also depends on the specifics of the charge that wanders into that field. The nice thing about electric potential, aka V, is that it depends only on the field strength. It doesn't conflate the specifics of those individual charges in there with that. I know that's a tricky point. Please, please, please feel free to come talk to me and ask me questions, because I know that that one is especially conceptually difficult. Now for number 3, again, our positive charges, our protons, will always move from high potential to low potential. They fall down the stairs. Our electrons are weirdos. They move from lower to higher potential, aka falling up the stairs. Guys, that's all I have for you. You've done great. This was a big ol' lesson. Feel free to watch again, ask me questions, blah, blah, blah. You know the deal. Have a great day.